Alright, in this video, we will find pi in honor of Pi Day. So I'm recording this on 3/14/116, or technically it's not perfectly Pi Day, but I think this is good enough. So it's Pi Day, let's celebrate by finding pi, or solving a sequence. So this is one called the Basel Problem, solved by Euler in, I think, like about 1750, maybe it was like 1755. And it's the value that this sequence equals. Let's see here. Alright, let's just write one more term. No, that's good enough. So what does this sequence equal? Well, this is not easy, I'll tell you that. Why is it not easy? Well, we'll see in a second. So let's just say it equals k for now. We're not going to be doing any easy math in this video. I hate to break it. We're just going to do really flippin' cool math. So let's talk about something else that involves pi. Well, if you're working in radians, alright, then, well, actually, it doesn't really matter at the moment. Oh, yeah, it does. So let's talk about sine as an equation. Sine is the y value at every point. If that was your point on a circle, unit circle that is your sine value if this is your angle right here. The sine of that angle. And that's how you'd calculate it. And so at every sine value, at every point, there's a different sine value. Now here's the interesting thing. Sine is 0 at this point and this point, right? There's no height here from the origin. There's just no height. Yeah. And so that is an angle of theta equals 0. Angle of pi. Angle of, how about 2 pi? How about 3 pi? You get the idea. And then it also goes the negative direction. Negative pi, negative 2 pi, so forth. So we know that sine of any one of those theta values is equal to 0. Cool. What can I do with that information? Well, actually, you may not have guessed it, but you can do a pretty interesting thing with that piece of information. So if you know a bit about quadratics, and you sketched a curve, let's say this was your curve for a second, and let's say it intersected at 1, -1, and 2, sure. Wait, -2, -1. Let's make this 0, let's make this 1. Let's just say it's that. So if your curve does something like that, you can actually set up an equation that looks like that. Alright, which sounds bizarre, but it's pretty straightforward. You just multiply by those points, because this is when the equation would equal 0 on a normal graph. Alright, so we should have 4 sets of zeros. So our first 0 we'll set up like this. X over -2. Yep. So if you plug this in, if you plug in -2 into this point, -2 divided by -2 is +1, and +1, 1 minus +1 is, well, needless to say, it's 0. So it would equal 0 at that point. And you just keep doing the same thing. You divide by -1 here. And right here, this is interesting. If you plug 0 into the equation, it equals 0, so x alone. There's nothing special there. If we divide by 0, we'd have problems, so this is what you substitute with. And then continuing on in this direction, 1 divided by x divided by 1. So let's simplify this a bit. There's 1 minus half x, except for the minuses combined to make a positive there. This is 1 minus -1 x, or 1 plus x. This is x, and this is 1 minus x. Good. Let's see if we get this shape. We should. That's when the equation equals 0. So 1 plus half x. Alright. And now we also have a 1 plus x. Then we also have an x. Oops, multiply. And then we also have a 1 minus x. So this equation should look roughly like this shape. It might go the opposite direction like this, but as long as it goes through those points, we're good. And check that out. That's just beautiful. You can see it go through each one of those points, just like we told it to. Oh, it's just so perfect. And so this trick can be used for the sine equation. If the sine equation equals 0 at all those points, then we can set up an equation that equals sine. So, using the same trick, and we'll have to use the trick where we multiply just by x at 0, because if x is 0, it all multiplies the whole thing to equal 0. So this is a very neat trick, and Euler used this beautiful trick to work with the sequence, but the sequence is coming up later. We still have a few more steps to do. So let's first try to represent sine. Sine is going to be an infinite multiplication, but whatever. So our first term is going to be x. We're going to start with 0. Now let's go in the negative direction for a second. 1 minus x divided by pi, negative pi. Then let's go in the positive direction. 1 plus x divided by pi. Oop, that's going to be minus. Sorry, it's always minus. And then we're going to go the negative direction again, except for this time to negative 2 pi. X over negative 2 pi. And then to the positive direction, 1 minus x over positive 2 pi. And so forth. This should equal sine. I put that dot dot dot. That's very important. This alone is not sine, it just estimates it. Alright. You can actually do some simplification here. I'm going to do that just so it graphs better. One simplification is get rid of the parentheses on x. Another one that is actually going to be pretty useful is if you multiply, here, this can be simplified to positive x divided by just pi, not negative. So you can always get rid of these negatives by making them positive here. And here's the interesting thing. If you group these together and these together, here, let's actually prove something real fast. Let's use this tiny bit up here. If I multiply a minus b by a plus b, what happens? Well, a times a is a squared. Negative b times a is negative ba. A times b is positive ba. And negative b times positive b is negative b squared. What happens? These cancel out, and all you're left with is a squared minus b squared. This is really neat, because what we have going on here is one number plus this number, and one number minus this number. Same thing here, one number plus this number, and then one number plus this other number. Even though it has an x, I'm still going to call it a number. So that means we can rewrite these chunks as 1 minus x squared divided by pi squared. Alright, and we can rewrite this chunk right here as 1 minus x squared divided by 2 pi squared, or 4 pi squared. This is incredible because it simplifies the thing very nicely, because this is taking the negative side and this is taking the positive side. So we're basically combining those zeros, and so you can keep on going here with more terms a lot easier, because we know the pattern. It'll just be 3 squared now, because we're going to have a 3 pi equaling 0. Let's put dot 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 over there. So 3 times 3 is 9, and pi times pi is pi squared. So you can expect that continues. Let's see if that is the sine function. Alright, so let's graph sine. Sine looks like that. Alright, you get it. Let's now plot this excellent equation. X times 1 minus x squared divided by pi squared. Then we're going to multiply that by 1 minus x squared divided by 4 divided by pi squared. Now we're also going to do 1 minus x squared divided by 9 divided by pi squared. And let's end it here. Let's see how well this looks. So there's our sine graph, and another other graph is going to graph right now. Check that out. It's crazy awesome that it works. It just continues from there. And so if you can imagine, the more terms we multiply, the more this flattens out and stretches along this whole curve. And this is just using this method. Therefore, this you can accept. If you went to infinity, because this has all the zeros, that's equal to sine theta. Cool. That is neat. Now, there's another thing though. And if you don't know calculus, this might go over your head for a second. Just bear with me. I'll try to explain it as intuitively as possible. So let's look at the slope. So let's draw sine. Alright. So let's say this is 0 right here. There we go. So let's look at this point. I'll tell you right now, the slope there is a positive 1. Alright? So the slope is 1 and the point is 0. Alright? So this is no slope. This is the first slope. Let's call it f. And then there's going to be f prime. That's how we're going to write the second slope. So this is f at the point 0. This is f prime at the point 0. Now we're also going to have f double prime at the point 0. Let's look at what that equals. Well, if the slope is 1, and as you continue, the slope is going to be 0 right there, and the slope is going to be 0 right there. So we're expecting a curve that looks like this. So the slope is now flat again at that point, and therefore the slope there is 0. Now if you keep going with this, guess what? This is, although that's a 0 slope, if it's 0, it's going to look like that. Except for now, right after that point, it's going to go downward. Because if you look, this is going into a negative slope here. So it's going to look like this going down. Like this going up. It looks just like the sine, which it should. And if you look, the slope there is a negative 1. If this is a positive 1, this is decreasing at negative 1. So f triple prime is negative 1. And guess what? Quadruple prime, that's not really the right word for it, but whatever, is 0. And it just repeats this series over and over again. Well, you can use this for your benefit. If we have an equation that matches this, then the equation is probably going to be equal to it. Let's see what we mean here. If we have the equation, let's see here, x, yeah, let's do that. So let's set f equal to x. If we take the derivative, then we get 1. Alright? And if we take the derivative again, we get 0. Well, that's a start. Let's add another term. Let's subtract this term. And let's make it, I'm subtracting it because of this guy. Let's make it x to the 3 over 3 times 2 is 6. There's actually method to my madness here. Alright, so now, if you plug in 0 into this equation, you get 0 at every point, therefore it just equals 0 at that point. If you plug 0 into this equation, even though there's nothing there other than the 1, it's just going to equal 1. So if you bring that down, it's going to be x squared over 3. If you don't know that, that's just a derivative. The slope of this guy is this. Just a simplification. Oops, 2 over 2, not 3. Bear with me here. And now if you plug 0 into that, that goes away, so that's good. And then if you take the derivative again, you get a positive x. That's a derivative of that guy. Oops, negative x. The negative sign stays. And then if you take a derivative again, this is perfect because you get 1. Well, negative 1 because of the negative sign. If you see what I'm doing, all I'm doing is setting it up so the slope of the x equation is 1. It's technically 1x. And the slope of 1 is just a flat line, and so it's 0. And then it goes away off to the distance. Now this guy, if we attach it on, it's still going to equal 0 every time you plug in 0 into this equation until this point, when after you take a derivative, it equals negative 1. That matches this guy. So we're slowly setting this up, and actually the pattern continues very nicely. You're going to make it positive this time, because this pattern continues 0, 1, 0, negative 1, 0, 1, 0, negative 1. And so this pattern will continue if we pick all the odd numbers, and then 5 times, here, the way you write it shorthand is 5 factorial. That's 5 times 4 times 3 times 2 times 1. You can see if every time you take the derivative, that number goes down. Then you multiply by 5 because of the derivative rules. Don't worry about it. And you get 4 factorial now. And then it keeps on going down. X to the 3 factorial over, x to the 3 over 3 factorial. Then we get x to the 2 over 2 factorial, which is just 2. Then we get f quadruple prime is equal to x over 1 factorial, or just x. Then if you take it a 5th time, check it out. The derivative of x is 1. And we know that the 5th derivative would be right here, and it's a 1. So we know if we set up an infinite series of these, all their slopes would match, because you'd keep on having equation, more of these terms to pull from when you take more derivatives. X is 7 over 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1, so forth. And continues from there. Let's check to see if it really does match up, and I'm not just making things up. Alright, so we have sine. That's going to graph like this. Yeah, you get the idea. Now we're also going to have just x. Then we're going to subtract this one because we have that negative 1 slope. It's going to be cubed divided by 3 divided by 2. That's how we're going to write it. Then x to the 5 odd numbers divided by 5 divided by 4, 3, 2, 1. We don't have to divide by 1. Now we're going to subtract the next term, x to the 7. X to the 7. And divide by 7, divide by 6, divide by 5, 4, 3, 2. And let's graph it. I'm getting a little bored here. Alright, so there's our graph. It gets 0 at every pi. Check this out. Comes right in. Swoops down and curves around. Comes out this side. It's just beautiful. Makes me tear up. That's just, oh, it's so wonderful. I can't articulate how amazing this is. So Euler noticed that both of these sequences equal sine. This equals sine because sine has these properties, and so does this f function. Let's call it f. Alright, so if we can have infinite two things are equal. Oops, let's make this, whatever. Let's go in here. This should be x. Alright, so sine x is equal to x minus x to the 3 divided by 3 divided by 2, or 3 factorial, plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial. If you know your calculus, this makes perfect sense. If you don't, just know that the slopes match up if you keep pulling this down. Alright, there you go. And sine also equals, as we found out, this infinite multiplication of x times 1 minus x squared divided by pi squared times 1 minus x squared over 4 pi squared. And then one more, 1 minus x squared 9 pi squared. Alright, and continues forever. These both are amazing in and of itself, but what happens next is truly incredible. Because those are both sine, those things are equal to each other. So let's write that on the next page. And you can kind of see where this is going. See that pi squared, and you see that 4, 9. That reminds me a lot of this sequence. Because that's 9, that's 4. The next one you can imagine is going to be 16. We have that 1 right here. Let's see where this goes. This should be quite incredible. Honestly, I lost my mind when I first learned this stuff. So, we got sine equals both those things, and both those things are x plus x squared over 4. no, x cubed over 3 factorial. This is a minus. Gosh, I'm messing up all over the place. And there's going to be plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so forth. Now there's going to be equal to the infinite multiplication of x squared. Now you should be scared of the infinite multiplication. There's an x here, sorry. Because how do you simplify something like that? Turns out Newton came up with a brilliant way of just collecting all the terms here. So it's x squared still, nothing changed there. And this is over 4 pi squared now. And so forth. I'm just going to end it there. So here is the interesting thing. This is all good, and you can leave that how it is. Yeah. But over here is where really interesting stuff happens. Alright? So just to simplify this whole equation on both sides, I'm going to divide by x. Everything here has an x, everything here has an x. So let's remove it. Alright, if we divide this side by x, it's now just 1 minus x squared divided by pi squared. And then 1 minus x squared divided by 4 pi squared. And so forth. Goes on. And then this is now x divided by x is 1. This is now 1 over, well, one of the x's is gone, so it's x squared. And 3 factorial is 3 times 2, 6. And then now it's x to the 5. Now it's x to the 4 over 5 times 4. I'm not going to calculate that. Let's leave it as 5 factorial. You get it. It just keeps going down. And then there's other terms. I'm going to leave those alone because there's a reason. There's something truly magical here going on. So if you multiply this infinite sequence of numbers, let's add one more here. You'll see why. That'll help us along. If you know your factoring, you're always going to combine a 1, and you're always going to combine these terms. That's going to get more complicated. And you're also always going to combine 1 and this, and 1 and this term. If you didn't see what I was doing, we're just matching sets. So we're going to have one of these, and we're going to have one of these. So we're matching all these numbers together. Now, if you notice, if we just keep on doing this forever, which we would technically, we're just going to get a bunch of 1s multiplying together. Hey, that looks pretty similar to that side. X squared plus x to the 4 over 5 factorial, so forth. Minus dot dot dot. Alright, and over here we got 1. So that's collecting all the first degrees, because that's technically x to the 0. And this is technically x to 0, whatever. But now, this is where the interesting thing comes in. We're not going to have any x1 terms. It's impossible. There's only x squared terms. So if we multiply by x squared, it's going to be x squared or x to the 4 or x to the 6 or any one of those. So we're going to expect the next one is going to have x squared terms. Now if we multiply any of these two together, we're not going to have an x squared term anymore. We're going to have x to the 4 term. So we know we can't multiply those together, but here's what we can multiply. 1 over here and this, and 1 over here and this. And you can keep on doing that when it gets more complicated. So you can expect, after you add those together, because those are separate multiplications, and so they just add together in the end, this is what we should expect. So a negative times a positive, we should expect a negative here. And we're going to get 1 over pi squared times 1 is 1 over pi squared. Simple as that. Then a 1 over 4 pi squared, we're going to, yeah, we already factored out the negative. It's going to be a 1 over 4 pi squared. Then guess what? We're going to also get a multiple of 1 over 9 pi squared. And we're also going to get 1 over 16, so forth. And this is all multiplied times the x squared term. And then everything gets more complicated over here. But here's the thing. Check this out. What exists on both sides? This messy stuff that goes into higher powers, that exists on both sides. What also exists on both sides? These guys. So here's what we're going to do. We're going to remove both of those. In fact, we're also going to remove this negative right here. So all we're left with is 1/6 x squared equals this series of things added together. 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared. And again, all we did was we collected the terms that would happen through multiplication. Try it out for yourself. Alright, and then that's times x squared. You can divide out the x squared, so we get 1/6 equals, let's factor out the pi squared. There's a pi squared in each of those. 1 over pi squared, that is. Then this is a sequence that says 1 over 1, taking that squared. This is a sequence that is technically 1 over 2 squared, 1 over 3 squared, and so forth. Let's multiply by pi squared just to get the sequence by itself, and we get pi squared on 6 equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc., etc. Look at that beautiful result. Holy cow. It's just remarkable. Alright, let's check this out though. Can we trust this? If you've looked at summation before, let's use my other calculator here. If you looked at summation before, these things simplify pretty amazingly. So let's try to find pi just to prove that this all works. So we're going to multiply everything here by 6, and then we're going to square root it once we do it. Alright? So this is how you write it. 6, because everything is multiplied times it, divided by x. That's like this. Oops, wrong number. X divided by x. Alright, and we're going to start at 1, because 1 divided by 1 squared, divided by x is the same as dividing by x squared. Alright, and now, let's take this to like 500, just to be serious about it. And then we're going to square root what value we get. And we should get something pretty close to pi. We won't get exactly pi, that's guaranteed. I mean, that's not really guaranteed. So let's check this out. So we multiplied everything by 6, so this is that sequence all multiplied by 6. And then we're going to square root it, so we just get pi by itself. So we're adding 500 terms here, because 1 to 500 is 500. Let's go. It's loading. Check this out. It's going to take a sec. Really, your heart should be beating here. It's going to come any moment here. If I didn't add 500 terms, it'd be happy with me. And there we go, 9.857. You're like, that's not pi, and then you forgot. We're going to square root that guy. Square root that answer, and we get 3.139. Let's round up. Alright. 3.14. And then you have all these other terms. That is pi right there. This should be blown up in your head right now. How is that even possible? And yet it is possible, because we have two sequences that equal sine, and then we combine them. There's nothing more amazing than this. This is just my favorite thing ever. It's called the Basel Problem if you want to look it up. And there's a variety of things out there that talk about it. Thanks for watching. Happy Pi Day.